In this video, we're going to focus on different terminology that revolves around the periodic table. So here is an example of a periodic table, and each box on this periodic table represents an element. For example, this box is hydrogen, this box is lithium, this box is beryllium. Well, for this periodic table, we use the term periods, and all periods mean are rows. So here's a period. So we have hydrogen and helium. It's our first period, our first row. Here's our second, third, fourth, fifth, sixth, and what we have down here, what we call inner transition metals. These actually plop right in here. So boop, get put in here. And what the periodic table looks like here is a condensed form. If you have these right in here, it makes it much wider. So they put them down at the bottom. And we have our seventh row. And the same here, these guys plop right in here. So periods are rows. And we refer to them as the number of energy levels that an atom will have. So for example, here is an atom. And our key right here, these little circles, these red ones are energy levels. Green is proton, orange is neutron, and blue is electron. So the electrons are on the energy levels on the outside. The protons and neutrons are in the middle. When we look at the periodic table, we're going to look at hydrogen here first. And for hydrogen, it is in row number 1 or period number 1 or energy level number 1. And we have the red here. It has one circle around it. And that is because it's in row 1 or period 1. So it has one circle. Whereas if we go down to, let's say, lithium here, it's in row 2/period 2. So you have two circles. So down here, sodium would have 3, magnesium would have 3 circles around it. Potassium would have 4. These guys will have 5, these guys will have 6, these guys will have 7 circles around it. Next, we have to talk about groups. Groups are just the columns. The columns. So here's 1 group, 2 group, 3, 4, 5, 6, 7, and 8. When we talk about groups, we skip this middle part, these transition and intertransition metals. And the big thing about groups is that they share the similar chemical properties. So they share similar chemical properties here. And we're going to talk a little bit more about that here in a minute. But before, we talked about periods or rows, and we said, hey, when we look this way on the periodic table, we look at the number of energy levels. Well, when we look at groups, we look at something slightly different. We look at what we call the valence electrons. So valence electrons are similar to electrons, meaning they have a -1 charge, but the difference between all the electrons in one atom and the valence electrons is the valence electrons are the electrons on the outermost energy level or the outermost circle. So for example, here hydrogen has 1 valence electron. And our lithium has 1 valence electron. So lithium here has 1, 2, 3 electrons total, but only 1 valence electron because there's only 1 on this outer energy level. So let's go over here at boron. So uppercase B. Uppercase B. We have 1, 2, 3 valence electrons because it is in group 3 here. But it has 5 electrons total. So 1, 2, 3, 4, 5 electrons total, but only 3 valence electrons. And what we can do is we can look at the different groups. So every element in this group will have 1 valence electron. In this group 2 will have 2 valence electrons. In this group we'll have 3, 4, 5, 6, 7. And over here, neon down will have 8 valence electrons. Helium's a little bit of an oddball. It will only have 2 valence electrons due to where it is on the periodic table. So helium's the exception, but every other element in this group will have 8 valence electrons. Well, what can we tell with these valence electrons? What can we show? Well, we can draw what we call Lewis dot diagrams. A Lewis dot diagram has an element symbol and the number of valence electrons. So the symbols, hydrogen's uppercase H, lithium's uppercase L, lowercase I, beryllium's uppercase B, lowercase e. And we look at the valence electrons depending on what group they are in or column. So let's look at beryllium here. The symbol is uppercase B, lowercase e, and it has 2 valence electrons. 2 valence electrons. So this is how we'd write it. Uppercase B, lowercase e, and we draw 2 dots. Each dot or circle represents a valence electron. 1, 2, because there's 2. All right, let's look at argon. Argon's over here. It has 8 valence electrons, and the symbol is uppercase A, lowercase r. So here's the Lewis dot diagram for argon. Let's look at carbon. Carbon's right here, has 4 valence electrons here. Let's look at carbon. We notice it has 1, 2, 3, 4 dots around the element symbol. So there's the Lewis dot diagram for carbon. So valence electrons have a -1 charge. All electrons have -1, but valence electrons also have that -1 charge. They're negative. Well, we use this when we talk about the octet rule. The octet rule means atoms want 8 valence electrons. There are some that only want 2, but octet means 8, so wants 8 valence electrons. They want to become like the noble gases over here. So here's our noble gases. They're happy. Noble gases are happy. They have 8 valence electrons in their outermost energy level. Helium has actually 2, is the exception to the rule, but neon, argon, krypton, and so on has 8. They're happy. Every single element wants to become like the noble gases. They want to be like them. They want those 8 valence electrons. So they will either lose electrons or gain electrons, whatever it takes. So let's look at lithium here. Here's lithium right here. Lithium has 1 valence electron right here in the outermost energy level. It has 2 options. It can lose that electron, so it can lose that valence electron, or it can gain 7 valence electrons. It's going to take the easiest route, which means it's going to deal with the fewest amount of electrons. So think about if you were to ever clean your room and do chores for your parents. Well, your parent comes to you and they say you can either have 1 chore or 7 chores. You're probably going to choose the 1 chore, the least amount. Well, electrons are the same, especially those valence electrons. So lithium will choose to lose that valence electron. So it lost it, which means the outermost shell is now full because this first shell can only have a maximum of 2 valence electrons, or 2 electrons. In this case, they're valence because they're in the outermost shell. It can only have 2. Lithium's an exception to this 8 valence rule. Let's look at another example. Here we have fluorine. Fluorine has 7 valence electrons because there's a 7 up here. So we can write fluorine like this for our atom. You have 1, 2, 3, 4, 5, 6, 7 valence electrons. Well, fluorine has an option. It can either gain 1 valence electron or lose 7 valence electrons. It's going to choose the smaller of the numbers. So it's going to gain 1 valence electron. And now it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons on its outermost shell, or energy level. So the big ticket things here when we talk about groups are each group has similar chemical properties. We're going to talk about the charges here in a minute. Electrons have a -1 charge. So 1 electron has a -1 charge. 2 electrons total have a -2 charge. So every electron has a -1 charge. Next, every element wants 8 valence electrons in its outermost shell / energy level. But there are some exceptions to this rule. You have hydrogen, helium, lithium, and beryllium. They are exceptions because let's say beryllium here, it has 2 valence electrons. Will it want to gain 6 or lose 2? It will want to lose 2, and it'll become more like helium and only have 2 valence electrons in its outermost shell. So here, this group had 1 valence electron. If it loses an electron, it's losing something negative. So now it's going to have more positive. If it loses 1 negative, it becomes +1. So think about it as doing the opposite. Loses 1, so -1 becomes +1. Opposites. This group here, what happens here is it becomes +2 because it'll give up 2 negatives and become +2, so opposite. Over here, +3. And these guys, they could either gain or lose electrons. So they could be plus or minus 4, somewhere in the middle, depending on the situation. The next group will become minus 3, then minus 2, minus 1, and the noble gases will be 0 because they're not going to lose or gain electrons. They're happy. They don't want to be touched. They're good to go. And based off these charges and what these elements will do, it really does affect that chemical property that they will have. So for example, lithium only needs to lose one valence electron or one electron. If it does, it's going to combine with another atom to do it. And because it only has to lose one, it's going to be very reactive. Same with your halogens over here, these purple guys. They're also going to be very reactive because they only have to gain one electron. Where, let's say this group, they have to lose 2 electrons, they'll be slightly less reactive than these guys.